welcome back everyone. So this marks really the last lecture of this whole school, and I welcome Professor Subroto for the last lecture of quantum dynamics, and over to you now.
Thank you very much. So this is, I guess, the last lecture of the school after the school's out. So thanks a lot for staying till the end. Okay, so let me just quickly, in a few minutes, wrap up what I was telling you in the last lecture, and then we'll move on to something else, which is sort of peripherally related to what I discussed in the previous lecture. So we concluded the previous lecture with a statement of the eigenstate thermalization hypothesis in terms of the expectation values of typical operators. And so the statement was that, not expectation values, I'm sorry, matrix elements of typical operators. And the statement was that if you look at the matrix element of an operator O between eigenstates M and N, then it has the following form. Where E bar is the average of the energies of the two eigenstates, and omega is the difference in energy. I should have written the H bar in the last lecture, which I didn't, so let me correct that. So that's E bar, and that's omega, and S of E bar is the thermodynamic entropy, which you can just obtain from the density of states. So it's like the log of the density of states. Okay, so this version of the eigenstate thermalization hypothesis says something about the matrix elements of physical observables. And as we discussed, the physical observables are defined over some region of this full system. And so the claim is that for a system which thermalizes, no matter what physical observable you take, which is defined over some finite region of the system, it's going to have a structure of matrix elements that looks like this. And so one can then, on the basis of this, come to a lot of conclusions about the nature of thermalization. You can show that there's an equivalence of ensembles and so on. So on that point, it turns out that there's also a slightly stronger statement that you can make, which is the following. So imagine that this is your full isolated physical system, and I look at a subsystem. So let's say this is the subsystem, and suppose you assume that the entire physical system, so let me just call this A, and let me call the rest of the system B, and like we've done before, and the full system is A union B. So A union B is the full system. Okay, and so let's assume that the full system is in some eigenstate of its Hamiltonian. So the full system, so A union B is in a state N, which is an eigenstate. Okay, so let me just even say in an eigenstate. Okay, so you.
Just one thing to I forgot to ask you yesterday. So, in yesterday's discussion, you didn't mention anything about the operator. So, like it could be any general operator.
Yeah.
So, in Ornov's lecture, he was talking about local operators.
Right. Yeah, exactly. So it is, okay, so this has to be in some sense a local operator, and the reason that it has to be a local operator is the following. I mean, one reason for it is this. So imagine that you take any Hamiltonian, right? Any quantum mechanical Hamiltonian, and so that's going to have a set of eigenstates and eigenvalues. So you have some eigenvalue equation like h hat acting on n is equal to En n. So now I can define projection operators. So the projection operator onto the state n, let me just call that P n hat, is just this, okay? So imagine that I consider two eigenstates which are very close in energy. One of them is n and the other is n prime. So let's say that I have h hat acting on n prime is equal to En prime, n prime, and suppose En prime is very close in energy to En. So I can now construct the projection operator corresponding to n prime. And so if I look at the expectation values of these projection operators, and if I look, for instance, at just one second, yeah, if I, right, so if I look at the expectation values of these projection operators, then yeah, so you can see that if I look at the matrix element of the projection operator P n hat in the eigenstate n, if I look at that matrix element, so that's clearly going to be 1. On the other hand, if I look at the expectation value of the same projection operator P n hat in the eigenstate n prime, that is going to be 0. Right? Because these are orthogonal states, but they're very close in energy. And so if you were to think of this now as O n n and this as O n prime, you can see that it's not a smooth function of energy at all, right? Because the energies are very close, but the values are very different. And similarly for P n prime hat. And so what happens with something like a projection operator is that if you then write it in the basis of your, whatever local degrees of freedom you have, you see that it's highly non-local. And so if you have highly non-local or non-local operators, then of course you could have a violation of ETH. So ETH then is specifically written for local operators. Okay. Right, so let me just get back to what I was saying, which is also related to, in some sense, what Shamik was talking about. So suppose that A union B is in an eigenstate of the system, which is n. So you can now ask, well, if the whole system is in an eigenstate, in what state is this subsystem? And so we know how to answer that question. So first of all, we know that because this is a quantum mechanical system, even if the whole system is in a pure state, a subsystem doesn't have to be in a pure state. The subsystem can be in a mixed state. In fact, it generally will be in a mixed state. And we also know how to obtain that mixed state. So the way that we obtain that mixed state is by first writing down the density matrix for the full system, and then tracing out the degrees of freedom of B to obtain the density matrix for A. Okay. So we can do this. And so a stronger statement in some sense of the eigenstate thermalization hypothesis is that if you were to do this for any arbitrary eigenstate, then what you would get for the density matrix of the subsystem is basically something like a thermal density matrix. So you would see that this would be where I'm assuming here that I can write down the Hamiltonian of the system, of the full system, as a part for A, a part for B, and some interaction between A and B, which in some sense is small. Okay, so if I can do that, it's either small or it's just confined to the surface and not the volume of A. And I'm also assuming that B can be taken to be much larger than A. It has a much larger Hilbert space dimension. Modulo all of these caveats, you can then generally argue that when you do this, it's going to look like the distribution for A, the density matrix for A, is a thermal density matrix with a temperature beta that is given by the energy of this energy eigenstate.
Isn't it slightly better to write that line as trace of B of e to the minus beta h of the full system? Because as you said, this HAB is not necessarily small.
Yeah, so okay. So if HAB is not necessarily small, then of course you can't really write it like this. I mean, just taking a specific case where you can do it. If HAB is not necessarily small, then you just write trace of B is, so this is some object, okay? You get this, and then this object that you get is basically going to be what you would have got if you then also, for instance, didn't do this for just this one particular eigenstate, but you looked in some window of, small window of energies about this eigenstate, did the trace over the entire thing, you would still get the same answer. So it's only really in, so if you wanted to insist that this was some e to the minus beta n h a hat, then you have to be able to write down the Hamiltonian in this way, and then make the following claims that the interaction is either weak or confined to just the surface. So you don't really have any strong long range interactions, and also that the Hilbert space dimension of B is quite a bit larger than the Hilbert space dimension of A, which incidentally is, so the way what you're saying here is that this is the equivalent of the way in which you get the canonical distribution from the microcanonical distribution, even for a classical system. The only difference is, so even there, right, when you're getting the canonical distribution for a classical system from the microcanonical distribution, you assume that the Bath part is actually large. You take that to infinity, and of course the system for which you're getting the canonical distribution can be as small as you want it to be. So that is really the rationale for this. But the interesting thing is that in the classical case, the way you would do this is to say that the full system is in some microcanonical state, right? So meaning that it has some uniform weight over some volume of states in phase space. Here what you can do is you can do it for a single energy eigenstate, and you will still get this canonical distribution. Okay. So this is in some sense, if thermalization seemed a little mysterious from looking at that formula, this way of looking at it should demystify it slightly, because you're now really talking about, you're looking at the same kind of situation that you would look at in a regular sort of setting that you learn about in statistical mechanics, system bath. And what you're saying is that the bath here can bring this system to thermal equilibrium, give it an equilibrium distribution, And the main thing here is that the system plus bath happens to be in a single quantum state, not in an ensemble, not in a mixed state, but in a single quantum state. And this is very different from what would happen in a classical system. So remember that a single quantum state of the full system is classically equivalent to having a single microstate. So what happens is that imagine that you had a classical system and you said that the classical system was in one single microstate, not an ensemble. And now you partition that system into a smaller subsystem and a bath. Okay? So if the entire system happens to be in a single microstate, even the subsystem would be in a single microstate. You will not be able to generate a distribution for a subsystem from a single microstate of the subsystem and the system classically. But quantum mechanically, you can do that. So that's a big difference in some sense between quantum thermalization and classical thermalization. Okay, so and again, from this one can then derive many things. For instance, one can argue that the thermodynamic entropy of the subsystem is equal to the entanglement entropy between the subsystem and the environment in this pure state of the whole system. So all of that can be done, and I'm not going to discuss that. What I will do when I give the organizers my notes is also give you a list of references where you can find those discussions. So one of the reasons that I bring this up is to basically tell you that in general, and you know this from your anything that you've studied in statistical mechanics, that it's important to look at systems that are not isolated. Because almost any physical system that you're ultimately interested in is exposed to some kind of environment. In order to develop the statistical mechanics of that physical system, of course, conceptually you need to think of that system plus the environment as an isolated system and then proceed. But really, as a practical matter, the system is coupled to an environment, and that's the reason that the canonical ensemble, for instance, is used so widely, because most physical systems happen to be at a certain temperature because they're brought to thermal equilibrium by some bath that they are coupled to. Okay, so this is sort of a lead-in point for me to tell you about very quickly, by very quickly I mean just the remainder of this lecture, about what happens when you have quantum systems which are not isolated, which are actually coupled to a bath, and these go by the general name of open quantum systems. So in the example that we were just discussing, you can think of A as being like an open quantum system because it's in contact with a bath B. So what we'll be looking at in this lecture is the dynamics of these open quantum systems, how these open quantum systems evolve. Now that is a topic in itself, not just for one particular module of a school, but perhaps for an entire school. There are many different aspects of open quantum systems, and there's certainly no hope in hell that I can summarize all of them or even any meaningful subset of them in just one lecture. So instead, what I'll do is I'll focus on one specific aspect of open quantum systems, which is the way in which the density matrix for an open quantum system evolves as a function of time. And so this is something that's called a quantum master equation. It's very much in spirit the same as classical master equations that you might have come across in other situations, in which you have a certain set of allowed states for a system, and you have some distribution over those states, some initial distribution, and then given some rules for how some external agency might induce transitions between those states. You can then write down some equation which tells you how that distribution evolves. So that's what we're going to do here for this kind of open quantum system. And so what we'll be looking at is how the reduced density matrix of this open quantum system evolves, given some properties of the bath that it is connected to. How do you actually write down some general evolution equation for the open quantum system, for the reduced density matrix? And that's something that's called a quantum master equation. And the specific form of that which we will derive and look at is something called a Lindblad equation. So I'll show you what the Lindblad equation is, and what you can, some elementary applications of it. So the statement of the problem is something like this. So if you go back to what I've drawn there, the full quantum system A union B, so that's a closed system. And so if I started out, let's say, that full system in some particular state. Now, just to keep the discussion very general, let me assume that the state of the full system was also not necessarily a pure state, meaning that even that full system was perhaps not fully isolated, something placed it in a mixed state. And so let's assume that A union B has a density matrix rho hat of T. And so we know, given the Hamiltonian of the full system, how rho hat of T actually evolves from rho hat of 0. So rho hat of T is equal to e to the I h hat T by h bar. Okay, which is basically the solution of the evolution equation for the density matrix. And I'm assuming all of you have seen this equation before, and just in case you haven't, this is basically the quantum equivalent of the classical Liouville equation. So this is classical for the phase space density, and this is the quantum Liouville equation, if you like. Okay. And one source of confusion for my students whenever I teach this in a quantum mechanics class is about why this has a partial derivative and why that has a total derivative. But I leave that as something for you to figure out if you're confused about why that's partial and why that's total. Okay? Anyway, so this is basically the solution of that. So here's the question. So imagine that you're given rho hat of 0. And so I can trace out the b degrees of freedom from rho hat of 0 and get rho a hat of 0. So that's a reduced density matrix at time t equal to 0. And so similarly, if I look at the density matrix at time t, I can again trace out the b degrees of freedom, and I can get the reduced density matrix of A at time t. So I know that there is, at least in terms of writing down, a reasonably straightforward evolution equation which connects this to this. The question is, what is it that connects this to this? Okay. So how do I write down an evolution equation for the subsystem? And the subsystem, mind you, is now an open quantum system. Its evolution in general is not going to be dictated by its Hamiltonian because it's coupled to a bath, right? Even if in the end its equilibrium distribution, as I wrote down, a steady state equilibrium distribution could only depend on its Hamiltonian. Certainly the evolution to that equilibrium distribution is not going to depend only on its Hamiltonian, because, I mean, this is like saying that even in a classical situation, you know that finally if a system is coupled to a bath and it evolves and reaches thermal equilibrium, it reaches the canonical distribution e to the minus beta h, but then the full evolution to the thermal distribution, of course, depends on the coupling between the system and the bath. And so it's the same thing here. So that's the question. So the question is, how does one obtain? So how does one obtain rho A hat of T given rho A hat of 0? And of course, that will depend on the properties of B and the coupling and so on. But is there any simple sort of equation, simple evolution equation that one can write down like that? And so it turns out that there is. It may not be as simple as the equation that I wrote down there, but there is a well-defined scheme that one can employ to proceed. And so this is something which, so I'll tell you what it is in just a second. But you might think that this, whatever I'm going to tell you, is something that would be many, many decades old, given that quantum mechanics is now 100 years old. It's going to celebrate its centenary next year. And this seems in some sense to be a pretty fundamental problem. I mean, people have known about reduced density matrices from the 1940s or something. You would have thought that this is probably something that people would have known for many, many decades. So it turns out that this, the way that this evolution proceeds is something that someone came up with only about 35 to 40 years ago, which might still seem like a long time ago. It's before most of you were born. I guess all of you were born. Most people in this room were born. But still, as far as given how long quantum mechanics has been in existence, compared to that, it's a fairly recent development. And so, what relates this to this is something that's expressed in terms of what are called Krauss operators. So this is something that's called the Krauss operator formalism. And the Krauss operator formalism is simply the following. So imagine that you're given any density matrix, or even forget about rho A. Just think of any density matrix, and you ask what are the properties of this matrix, of this operator defined in a Hilbert space that specifically make it a density matrix. So there are really essentially three properties which make an operator defined in a Hilbert space a legitimate density matrix. It's when it satisfies these three properties that you can actually think of it as a density matrix. So the three properties are a density matrix that 1, it has to be Hermitian. 2, its trace has to be 1. And 3, it has to be positive semi-definite, which means that its eigenvalues have to be greater than or equal to 0. And so you can see that this condition implies that the eigenvalues are real. This condition implies that the eigenvalues are not just real, that they are positive in between, that they're non-negative. And then the fact that the trace is equal to 1 tells you that each eigenvalue has to be between 0 and 1. And so in some sense, those eigenvalues can be interpreted as probabilities in some appropriate basis. But really, it's these three properties of the operator that make the operator a density matrix. So the Krauss formalism is the following. It tells, so you can ask the following question. Given some operator at time t equal to 0, which has these three properties, what is the most general kind of evolution which is going to preserve these three properties? So the Liouville evolution is certainly one kind of evolution that preserves these three properties. I mean, that's something which you learn about in quantum mechanics, but is there something more general which does it, of which the Liouville evolution is a special case? And it turns out that there is, and that is really the Krauss formalism. So the Krauss formalism says the following, that the most general kind of evolution that preserves these three properties is of the following form. So rho hat of t is equal to summation over A, and I'll tell you what this is in just a second. Excuse me. With okay. So it tells you that the most general evolution which preserves these three properties is in terms of these operators MA, and the evolution is given by the sum. So this is your density matrix at time t equal to 0. These operators of course are time dependent. And so when you write down the sum over these operators, the sum involving the density matrix and these operators, that gives you the most general kind of evolution. And these operators have to satisfy a constraint, which is that the sum over the product of their Hermitian conjugate and the operator themselves, the operator itself, is equal to the identity. So this is the most general evolution, and the maximum number, so the sum A is over whatever number of operators are required to describe the evolution for that particular physical system, and the maximum possible terms in the sum. So the maximum possible value or the maximum number, oh, by the way, these operators are what are called Krauss operators. So MA of t is a Krauss operator, and the maximum possible number of Krauss operators is d squared, where d is the Hilbert space dimension. And so it's not entirely trivial to show this, that the maximum
Hilbert space dimension of the reduced thing or the full?
is it, sorry?
Hilbert space dimension of
No, okay, so right now forget rho. Yeah, so right now forget about rho even being a reduced density matrix. Think of some system in a Hilbert space of dimension d, and right. So d is the dimension of the Hilbert space. For the specific case where the system in question is a subsystem A of a full larger system A union B, it's a dimension of the subsystem A. Okay, so this is the Krauss formalism. So now you can see that if the system in question is a closed system with a Hamiltonian, then you have just one single Krauss operator. So for a closed system, you have just one Krauss operator, and that Krauss operator m of t is just equal to e to the power of minus I h bar t, sorry, I h hat t by h bar. It's just the unitary operator. But more generally, you have more, and in principle, you can have a maximum of d squared of these. So this certainly is not as simple as unitary evolution, but it's also not very complicated. I mean, at least in terms of writing down what the general form of the evolution should be. The complication would of course arise in calculating what the Krauss operators are, obtaining what the Krauss operators are in some specific situation, given the properties of, given some description of the system in question and also what it's coupled to, and we'll look at some examples of that. But before I do that, let me now show you how one can start with the Krauss operators and actually derive this master equation that I was talking about, So the master equation would be whatever it is that has to replace the Liouville equation for an open quantum system, and whatever master equation we get, if we then impose the restriction on that equation that it actually has to describe a closed quantum system, we have to get back the Liouville equation. Okay, so the way that we do this is the following. So we are going to obtain an equation for the density matrix at time t plus delta t in terms of the density matrix at time t. So for those of you who have seen this kind of thing in the context of classical master equations, you know that if there's a situation in which the distribution over whatever allowed states at time t plus delta t only depends on the distribution over those states at time t, then it's what's called a Markovian evolution. So what I'm going to write down here is also going to be a Markovian evolution, but for the density matrix of the system and based on the Krauss operator formalism. So the idea is basically that we are going to write down some expression for d rho hat dt in terms of some operator that's acting on rho hat, and the expression acting on here is in quotes, and you'll see why after we get the full expression. But this operator rho L hat that's acting on rho hat is what's called the Lindbladian, or also sometimes called the quantum Liouvillean. So we'll actually derive an explicit expression for this in terms of quantities that we obtain from the Krauss operator. So we'll start from the Krauss operator formalism and get to this. Okay, so the way that we proceed is the following, that so we're going to write down rho hat t plus delta t in terms of Krauss operators. So okay, so in my notes I suddenly switched notation from using I for the summation instead of whatever it was that I used earlier. So sorry about that. I think I did an A earlier. No, I've jumped to I. Okay. So this is what we can write down, because this is a general form of the evolution. And what we want to do is we want to convert this ultimately into an equation of this sort, which means that what we want to do is on the right hand side, we want to write the right hand side ultimately as rho hat of t plus something acting on rho hat of t times delta t, right? And then of course it's going to look like what I wrote down here.
So earlier we had t as an argument of the Krauss operator.
Yeah. Sorry, I didn't write. It is there. So it's really right. So this is really so there's an argument of the Krauss operator which is t and delta t, because it's a Markovian process. So
does the right hand side have an overall delta t?
Does the right hand side have
An overall delta?
Yeah, it will. So right. So basically, I should have. So the m I hat that I've written is really some function of t and delta t.
Okay,
right. And what I'll do is I'll just write this down to first order in delta t. Okay. So then if you want to write this to first order in delta t, then you can argue that whatever number of Krauss operators you have, you're going to have one which is of the form. So let me just write this down and then I'll tell you why that's true. So you're going to have one which is of the form the identity plus something of order delta t, which I'm going to call m0, and then the other ones, whatever number you might have, are going to be of order square root of delta t. And you can see that it has to be of this form, because imagine that there was no evolution, right? Like whatever it is that was causing the evolution was turned off, then you know that your rho of t hat plus delta t would just be equal to rho hat of t. So if you're going to say that the general form of the evolution of rho hat is like this, and you want to write it down to order delta t, then it has to be that one of these operators has the identity plus something of order delta t, and the other ones can only be of order square root of delta t, because you get one factor square root of delta t from here, one factor square root of delta t from there, and so you're going to get delta t on the whole. So this is going to be the form of these Krauss operators if you want to expand the right hand side to order delta t.
So Subroto, just perhaps a stupid question. So earlier you had written rho of t is equal to summation over MIT rho t MIT. No?
Right.
Rho zero.
Yeah.
Rho 0 MIT, but now you have transported the t from MI
Right.
to.
Yeah. So the thing is, I mean, it's like saying that I could just as well here have written rho hat of t1 is equal to summation over a m hat of t1 comma t2 rho hat of t2 ma hat dagger of t1 comma t2. So that's what I've done here. I mean, so now my t, so when I write t1 comma t2, so the t2 now is t, and the t1 is t plus delta t. Yeah. Okay. So you have to be loud. Yeah.
Oh, sorry, I don't understand this order square root of delta t relation, because if I, let's say, consider this mt to be this exponential I ht over h cross, and I just like Taylor expand, the first term is identity.
So if you Taylor expand, and then
The first term is identity, and the second term is order t.
Right.
It's not square root t, right?
right.
Then how are you getting?
No. So you're saying that if you take e to the power of, if I understand you correctly, you're asking if I were to do this for e to the power of minus. Okay, let me put a delta t here, and if I do the Taylor expansion, then the first term is identity, and the second term is minus h bar delta h hat delta t by h bar, right? So that's exactly what this is. So that's what this quantity is. But further now you have these other quantities for which if you want those to be of order delta t as well, then they have to be square root of delta t and square root of delta t. So note that there is no multiplication between m naught and mi. So there's nothing that you'll get to order square root of delta t.
So this question is that in this case there's no mi not equal to 0, right?
No, so there's no m.
Mi not equal to 0.
Right. In this particular. Right. So in this particular case that Arnaud said, you only have the m naught. You don't have this. There's only one. So like I told you earlier, if you had unitary evolution, then you have this one single Krauss operator, and that's this. But when you have more, then those other Krauss operators will have to have this form. Okay. So So this is basically, so m naught is the identity plus something which is of order delta t, and some operator, when I say something of order delta t, it means some operator into delta t, and these are of the form some operator into square root of delta t. So let's just write that down explicitly. So what I'm going to do is I'm going to write m naught in the following way, and you'll see why I'm doing that. So I'm going to say that m naught, this operator is the identity plus some operator times delta t, and that some operator times delta t I can always write as minus I h hat divided by h bar plus k hat times delta t, where h hat and k hat are some Hermitian matrices.
Then you have to have an I in front of K.
Okay.
Sorry, I'm a bit confused. H hat has an I in front of K, but sorry.
Yeah, H hat has an I in front of it and K hat does not.
Oh, I see. And they're both Hermitian.
And they both. So I can write down any general matrix as some Hermitian matrix plus I times some other Hermitian matrix, right? That's what I'm doing here. And so the choice of notation is deliberate because you can see that in the case where you have Hamiltonian evolution, then you would only have M naught, and this would actually be the Hamiltonian, and this would be equal to 0. But I'm saying that in general, just write M naught as identity plus some matrix times delta t, and that some matrix I can write down as the sum of a Hermitian matrix and I times another Hermitian matrix. Okay. Now, as far as these other matrices are concerned, the MIs are concerned, so I'm going to write those down as I naught equal to 0. I'm going to write those as some delta t times some matrix Li hat. Okay, and these, of course, don't have to be Hermitian or anything. These are just some matrices. Right. So that's the way in which I write these. And then, of course, remember that I also have this condition that summation over I, Mi hat, Mi is equal to the identity. So this was the condition that I had. So that tells you that all of these matrices that I've written down are not independent of each other, right? So you can substitute these expressions into this sum and demand that it's equal to the identity, which means that whatever you get after you do the substitution to linear order has to be 0. Linear order in delta t has to be 0. And so that's going to give you the following condition, that k hat is equal to minus 1/2 times I naught equal to 0, Li hat dagger, Li hat. So that's what k hat ends up being because of this condition. So you can stick that in here. So now, having obtained these matrices, right, the forms of these matrices, now you can put them back into that equation there, which gives you rho hat of t plus delta t in terms of rho hat of t, and then take the limit. So you get something to linear order in delta t, and so you get rho hat of t plus delta t is equal to rho hat of t plus some operator times delta t. Take the delta t to the other side, take the limit going to 0, and you're going to get an expression for d rho dt. So you can do the algebra. It's not difficult at all. So when you do the algebra and you obtain the final expression, you'll see that it has this form. So d rho hat dt is equal to minus I by h bar plus j greater than 0 minus 1/2 of where this here is the anti-commutator. So this is the anti-commutator. So that's the evolution equation, and this is what's called the Lindblad equation. Some of you might have heard this name before in the context of some quantum system being put in contact with a heat bath. so this is the Lindblad equation, and the LJs that we have defined here in terms of the Krauss operators. So those LJs have a name. So the LJs are what are called the Lindblad jump operators. Okay. So this is the equation that replaces the quantum Liouville equation when you have an open quantum system. And of course, you can see that it does reduce to the right limit when your system is closed. So if the thing which you were assuming as an open quantum system was actually closed, then you wouldn't have any of these jump operators, because you have this one Krauss operator, which is just the unitary. And so in that case, the second term is gone, and you just have the first term, which is the usual quantum Liouville equation. Great. So just like one can write down this Lindblad equation for the way that the density matrix evolves for an open quantum system, you can also write down the equation for how any operator evolves as a function of time for an open quantum system. So if you have a closed quantum system, then you know that the evolution equation for closed quantum system.
So one is, in deriving this equation, we have explicitly assumed that the evolution is Markovian.
Yeah.
Okay, that's
Yes.
one.
Yes. Absolutely.
Secondly, there is I think it's an alternative derivation of this Lindblad equation starting from the full system and
Right.
then invoking a number of approximations, Born, Oppenheimer, etc.
Right.
So that's an alternative way of doing
Yeah.
it?
So basically, the whole Markovianness was in this coming from my assuming that you can write m naught and mi in this way with the h and k only depending on the particular value of time. So yeah, so what you could do, for instance, is you could actually carry out the much harder procedure. Suppose you didn't know anything about Krauss operators, but you knew how sort of a general system would evolve, system plus Bath, a closed system. And so then you start with the unitary evolution of the full system, and then you trace out the degrees of freedom and try to get this equation. And there, of course, in principle, you would have some memory function which you would get just like you do in the case of a classical system. And then at that level, you would have to put in the Markovian problem. So that is the way in which something called the Redfield equation is derived, which is also another way of looking at the Lindblad equation, but with some further approximations. But here I've sort of swept all of that under the carpet by using the Krauss formalism and making that assumption. Okay, so for a closed quantum system,
So you're implicitly assuming that the path has a, how should I say, much wider energy bandwidth in the system.
Yeah.
Then it's okay.
yeah. I mean, this is a general approximation of what makes a system Markovian, right? Like, in reality, so what this means is the following. So imagine that you have the system and you have a bath, and then what happens is that the system is coupled to the bath. So in some sense, information from the system goes into the bath, but it's a two-way street. So it can also come back, right? And this is really, even for a classical system, what underlies fluctuation dissipation finally. So here what you're assuming is that any information from the system that's gone into the bath gets dissipated into the bath over some very short time scale, and any time scale of the system that you're interested in is much longer than that. I mean, very qualitatively speaking, that's the way you're justifying the Markovian. Okay, so for a closed quantum system, you know that the way that an operator evolves in time is this. So the difference between the way the density matrix evolves and the operator evolves for a closed quantum system is just in the sign here. right? And that's also exactly what happens in classical mechanics when you use a Poisson bracket instead of a commutator. And so you can do exactly the same thing for an operator. So you have, for any general operator, again, you have a Krauss evolution. So the Krauss evolution for an operator turns out to be of the form O hat of t is equal to summation over so summation over I So it looks exactly the same as that for the density matrix, except that you have the dagger here and the undaggered operator there. For the density matrix, it's switched, just like here. And so you can go and turn the crank and derive a Lindblad equation for the evolution of an operator. And so that turns out to have a form that's similar to the Lindblad equation for the density matrix, but with certain things, certain signs changed. Because, right, certain signs means specifically just one sign change. So d O hat dt is equal to I by h bar plus this signs change, and in this particular term, the dagger and the undaggered operators are interchanged. So that's the evolution equation for an operator in this Markovian limit, the Lindblad equation for the evolution of an operator. So in some sense, at least in this Markovian approximation, that's all there is to the way in which an open quantum system evolves, at least in terms of the formalism. The main challenge is to obtain these Lindblad jump operators for a given physical situation, or also, if you like, to think in terms of the Krauss operators in a given physical situation. So in the remaining 30 minutes that I have, I'm going to just present a couple of physical situations to illustrate how this formalism can be used, and just to keep the discussion simple, but also very relevant to things that people are doing now, by which I mean, quantum computation and quantum technology, and looking at the stability of qubits. The system in question, at least for the first couple of examples, is just going to be a single two-level system. You can think of it as a spin half, you can think of it as a qubit, whatever it is that you like. And so we're going to assume that that is coupled to an environment or a bath, which is going to do certain things to it, depending on the nature of the bath, depending on what kind of bath it is. And then we'll see how that evolution can be described in terms of Krauss operators or the Lindblad equation. So that's sort of the general setup: single qubit, plus this is set to pi. Single qubit and in contact with an environment. So whatever, let me just say. So let's say this is your qubit, and then this is some environment. Qubit, and this is system A, and that is system B. Right. So in our discussion of ETH and the approach to thermal equilibrium, one of the important things was dephasing. Remember, dephasing is the thing which erases information of the initial state. And that's of course very important for thermalization, because when a system thermalizes, you want it to thermalize from any initial state, and you don't want the expectation values corresponding to these physical operators to have any memory of that initial state. But when you're dealing with individual qubits, on the other hand, for practical uses of these qubits, this process of dephasing is very bad. And the reason that it's very bad is that if you just think of what phase information for a qubit means. So now this is just a single qubit, which means that any state of this qubit is of the form some A up plus B down, right? And so A and B are the amplitudes for up and down. And the phase information of this qubit is basically contained in the phase difference between A and B. And so you know that that phase information is very important, because imagine that your A and B both had the magnitude of 1 over square root of 2. If they also had the same phase, then that would correspond to a state of the qubit which is pointing, say, in the right direction, meaning it's an eigenstate of the Sx operator with eigenvalue plus 1. If the phase was minus 1, it would be the other way. If the phase was pi by 2, then it would actually be an eigenstate of Sy. And for some other phase, it would be the eigenstate of an operator pointing in some other direction. So the phase information is crucial for a qubit, because it really defines the full state of the qubit. And so if that is gone, then that could be a problem if you're going to use the state of the qubit for some quantum computation operation or something like that. So dephasing is actually a huge problem for qubits, and one of the things that people who try to build practical quantum computers have to worry about is basically dephasing, and how to try to prevent dephasing to the extent that they can. So what we're going to do is we're going to look at dephasing due to an environment in this formalism. So the specific model for dephasing, which is what's called a dephasing channel. So incidentally, any evolution of a density matrix in terms of a set of Krauss operators is what's called a quantum channel. So in quantum information theory, this is the standard terminology, that it's called a quantum channel. And so the channel which describes dephasing of a qubit, or the action, the kind of environment which gives you dephasing of a qubit, does the following thing to the qubit. So if the qubit is in some state, is in the state 0. So let's say 0 is like downspin and 1 is like upspin. So imagine that the qubit is in some state, is in the downspin state. Then the dephasing channel does the following. It doesn't change the state of the qubit. So it doesn't flip the qubit from 0 to 1, but instead it does the following thing. So with the probability of 1 minus p, nothing happens. So let me just write those down. Okay, so let me just write down this equation, and then I'll explain the meaning. Okay, so we assume that the qubit at, before the action of the environment is, let's say, in the down state, so it's in the state 0, and the environment is in some state, right, which I'm just going to call 0. The environment doesn't have to be a qubit. I'm just calling it the 0 state of the environment. So so the qubit is in the 0 state. The environment is in some 0 state of its own, which is, some state of the environment. And so this is an unentangled state between the qubit and the environment. And then the action of the environment on the qubit puts the full system in this kind of state. So with a probability of P, the environment moves to a new state, which I'm calling 1 for the environment, and with a probability of square root of 1 minus, sorry, with a probability of 1 minus P, the environment continues to be in the same state, and so then you have a superposition of these two states. So that is the action of the environment on the qubit if the qubit happens to be in the 0 state. On the other hand, if the qubit happens to be in its 1 state with the environment also initially in 0 state, and then the action between the environment and the qubit takes place, then what happens is that you go to a state so then again there's no flipping of the qubit. The qubit continues to be in the 1 state, but the environment changes again with a probability P from the 0 state to some other state, which is 2, and with the probability of 1 minus P, it remains in the same state that it was. So you'd say, fine, okay, you write this down, but it looks like nothing is happening to the qubit, right? I mean, whatever is happening to the environment. So how is any dephasing or anything happening to the qubit? And the reason that something does happen to the qubit is that if you now take superpositions of 0 and 1 and look at what this means for superpositions of 0 and 1, you can see that an arbitrary superposition of 0 and 1 is not going to be left invariant. Like here, if it's in the 0 state, then it continues to be in the 0 state, the only change is that of the environment. Similarly, if it's in the 1 state, it continues to be in the 1 state, the only change is that of the environment. But if you now take a superposition, alpha 0 plus beta 1, alpha 0 a plus beta 1 a times 0 e, and look at what happens to that, right? Because these are different states, that state is not going to be in the same alpha 0 a plus beta 1 a after the action with the environment. And this is what causes dephasing here. So this is what's called a dephasing channel. And is a very important source of lack of loss of information for qubits. So one can actually write down, so remember that our goal is to sort of look, so this is the evolution that we know for the full system, A plus the environment, and from this we just want to extract that part which we can apply to A, the Krauss operators, and then forget about the environment. And so it turns out that for this kind of evolution, there are 3 Krauss operators, and the reason that there are 3 Krauss operators is that there are 3 different states that the environment can be in. It could either be in the 0 state or in the 1 state or in the 2 state, and it turns out that there's 1 Krauss operator corresponding to each one of these states, and the Krauss operators are rather simple. So the M0 operator is equal to square root of 1 minus P times the identity. The M1 operator is square root of P, and the M2 operator is square root of P 0, 0, 0, 1. So these are the 3 Krauss operators. Our system is just system A, it's a single qubit. In principle, there could have been a maximum of 4 Krauss operators. For this process, there are 3 Krauss operators. Okay, so we have the Krauss operators. So that's all we need in order to see how a particular initial density matrix state of this qubit evolves as a function of time, or evolves because of the action with the environment. So if I start with some initial state, rho hat, which is, it's a 2 by 2 matrix, and you know that rho 0, 0 and rho 1, 1 are real because this is a Hermitian matrix, and sum to 1 because it has trace 1, and these are complex conjugates of each other. So this is the general form of the density matrix of a qubit. So this is rho hat, those are the Krauss operators, and as a simple exercise you can check that these Krauss operators do indeed obey the condition that I had written down earlier, which was this unitarity condition that summation over I mi dagger mi should be equal to 1, and so that's satisfied for these. Okay, so then if you stick all this into the Krauss evolution equation, what you will find is that rho hat, after the action of these Krauss operators on this state, the new rho hat is going to be equal to rho 0 0 1 minus p, rho 0 1 1 minus p, rho 1 0 rho 1 1. Okay. So this is, so you imagine that you're starting with this initial state, and then the Krauss operators act because you have some interaction with the environment. This is the state that the qubit evolves to. If it interacts again with the environment, so you can see that the interaction leaves the diagonal elements unchanged. The off diagonal elements just pick up a factor 1 minus p. If it acts again, then it becomes 1 minus p squared, and then 1 minus p cubed, and so on. And you can see that if you have repeated interactions with the environment, and p is a probability, so 1 minus p is between 0 and 1, eventually the off diagonal elements just go away, right? And all your phase information in this original density matrix was contained in the off diagonal elements. And so the off diagonal elements are now gone, and so the system has dephased. Okay, so this is the dephasing channel, the simplest kind of dephasing channel for a qubit. And in terms of Krauss operators, this is what you get. So one can also think of this continuous interaction with the environment in terms of time, meaning that you say that every interaction with the environment lasts for a small interval of time delta t, and then of course you take delta t to 0, like it's all instantaneous, and so over some interval of time t, what happens? And so that is just taking the continuum limit of this, or in other words, solving the Lindblad equation. So I will again leave it as an exercise for you to start from these jump operators, start from these Krauss operators and derive the Lindblad jump operators, and then solve the Lindblad equation and get rho of t as a function of rho of 0. But we can already see what's going to happen just from here, because what we're saying is that there is now a dephasing rate. So this probability that we have, right, is now some gamma times delta t, right? So there's a certain rate at which the dephasing is happening, there's a certain rate at which the interaction is happening. And so if you plug that in here and you say that there are n such interactions in the limit that n goes to infinity, what you'll have is you'll have rho hat is equal to rho 0 0 times 1 minus gamma delta t to the power of n, rho 0 1, 1 minus gamma delta t to the power of n, rho 1 0, rho 1 1. And if you say that this interaction happens for a time t, or in other words, n times delta t is equal to some time t, and you're taking delta t to 0 and n going to infinity, then expectedly these become exponentials, right? So So your dephasing is basically happening over a time scale which is 1 over gamma. And as I said, as an exercise, you can also get the Lindblad jump operators from those Krauss operators and plug those into the Lindblad equation, solve the Lindblad equation, and check that this is indeed the solution that you would get. Okay, so this is a simple example of the application of the Krauss formalism and, if you like, the Lindblad equation to a physically pretty elementary system of a single qubit, but undergoing a particular kind of interaction with the environment, which produces dephasing. Yeah.
So you said, can
You said that the phase information are on the non-diagonal. Can you just
Okay, so all right, so how about I leave that as an exercise for you, so you can, so imagine that you have some state of the qubit, right? Now construct the density matrix and see where this phi ends up sitting. Okay, so it's going to sit in the off-diagonal matrix elements, as you can all see automatically from here. And so that is what you mean by dephasing, that information is gone. Okay, so this is one kind of bad thing that can happen to a qubit, which you can describe using this formalism. Another kind of bad thing which can happen to a qubit is something called amplitude damping. So there is another important channel relating to qubits that people working with them have to worry about, and that's called the amplitude damping channel. So the amplitude damping channel is actually even simpler in some sense to describe. So it's the following. So again, you have an initial state which is a 0 for the qubit and some 0 for the environment. If this is your initial state, then the action with the environment does absolutely nothing. It just leaves it invariant. On the other hand, if your initial state was the one state of the qubit with the 0 of the environment, then what it does is it puts it in this superposition. So if the qubit is in the state 1, then with probability p, it can make a transition to the state 0. So now you actually have a flip of the qubit in this basis, unlike in the previous case with the probability p. And when that happens, the environment also changes state from 0 to 1. And then with probability 1 minus p, nothing happens. It continues to be in the same state. And so this actually has a nice physical picture. So imagine that these are the states of your qubit. So this is the 0 state, and this is the 1 state. So this is a process in which if the qubit happens to be in the 0 state, then nothing happens. The environment remains as it is, and the qubit also continues to be here. On the other hand, if the qubit happens to be in the 1 state, then with a certain probability 1 minus p can continue to be in the 1 state with nothing happening to the environment, or with a probability p, it can actually make a transition to 0 with something happening to the environment. And so this really describes the process of spontaneous emission. So you have a ground state and an excited state, and what this process is telling you is that if your system, the qubit, happens to be in the ground state, then nothing happens. If it's in the excited state, there's a certain probability for it to continue to be in the excited state with nothing happening. Or if it makes a transition to the ground state with a certain probability, then something happens which changes the environment. And that something in this case is like the emission of a photon or something like that. So this is called the amplitude damping channel. So you can again write down the Krauss operators for this. This actually has just two Krauss operators. So the first Krauss operator is this one, and the second Krauss operator is that. Okay, so that's it. And so again, like in the previous case, starting from some initial density matrix, you can calculate what density matrix you'd get because of the action of these Krauss operators. So let me just write that down quickly. So rho hat in this case is going to be rho 0 0 plus p rho 1 1 square root of 1 minus p rho 0 1 square root of 1 minus p rho 1 0 and 1 minus p rho 1 1. Okay. So unlike in the previous case, okay, so like in the previous case, you can see even in this case you get defacing. So you have this factor of square root of 1 minus p times the off diagonal element. So if you repeatedly act with these Krauss operators, you're going to pick up higher and higher powers of square root of 1 minus p. The difference here is that here you have square root of 1 minus p, there you had just 1 minus p. But regardless of that, you can see that as you have more and more interactions, the off diagonal terms are going to become smaller and smaller. And so defacing is going to occur even here, right? But the additional thing that happens here that doesn't happen there is that even this is going to get smaller, okay? And that's to be expected, because if you think of what this is describing physically, it's actually describing spontaneous emission. So if you, let's say, had your system, if you started it out in the excited state and those sort of repeated interactions with the environment, eventually, of course, it's just going to end up in the ground state. So that's what's happening here. And so you can write down the continuous time version of this either by doing what we did there, which is to say that P is equal to gamma delta T, and again some n times delta T is equal to T. You take the limit n going to infinity, delta T going to 0, and then what you find is that rho hat of T is equal to 1 minus e to the minus gamma t rho 1 1, e to the minus gamma t by 2 rho 0 1, e to the minus gamma t by 2 rho 1 0, and e to the minus gamma t rho 1 1. So either directly from here or obtaining the Lindblad jump operators, put that into the Lindblad equation, solve it, and you get this. And sure enough, you can see that as t goes to infinity, everything is going, so this is gone, this is gone, this is gone, and this part of this is gone. And so in the limit that t goes to infinity, your rho hat of t is just 1 0 0 0. Okay? So what's happening here is that you have dephasing, but you also have this transition. You also have a transition from the 1 state to the 0 state. Whatever weight you had in the 1 state initially is ultimately getting transferred to the 0 state. So this has two kinds of things that are happening. So this is dephasing. What's happening to the off diagonal elements is dephasing. And the time scale for that in this example is 2 by gamma. Okay? So that time scale is what defines something called the dephasing time scale. And in the terminology of quantum computing, NMR, and also various other fields which deal with such dynamical measurements, that time scale is called T2. So if you go to talks on quantum computing, and especially people who talk about qubits, this is something which you keep hearing. They keep telling you about the T2 of their qubits. So T2 in this case is just the time scale over which dephasing happens, sometimes also called the decoherence time, and that here is 2 by gamma. Whereas there's also this other time scale over which you have the transition from the 1 state to the 0 state. That, if these states actually were at different energies, is something which involves a change in energy. This thing doesn't, but that one does. So that actually corresponds to a dissipation. It corresponds to a loss of energy, or sometimes, as people call it, a relaxation. So that time scale is the dissipation time scale. And is called T1, and in this particular case, T1 is 1 over gamma. So these are sort of the two important time scales that one typically associates with qubits in any quantum computing platform, T1 and T2. So one of which has to do with, just bit flips, if you like, a 1 flipping to a 0, and the other one has to do with dephasing. And both of these are bad, for the stability of a qubit, because not only do you not want the 1 flipping to a 0, you also want the phase information to be preserved. And so the idea is in general to try to make these two things as long as possible. In this simple example, they're related to each other, that one is just twice the other, but in general, that's not the case. Okay, so, right, so.
Amplitude dephasing because you lose information about the assistant. Why is it called amplitude dephasing?
Why is it called amplitude? Okay, so it's called amplitude damping simply because the amplitude of the one state is changing. And here, so the okay, so if you look at the density matrix, then generally the diagonal elements are called the amplitude elements and the off diagonal elements are called the phase elements. So here, because you have a change of the diagonal elements, you have amplitude damping, but you also have phase damping in this. Okay, so I have another 4 minutes, 3 minutes according to the, yeah, so sorry, you have to speak up. Sorry, how do you do what?
How do you choose the number of cross operators required? Like in this case, this 2 and
How do you choose how many Krauss? Right. Okay. So that I didn't. So in examples like this, the number of Krauss operators that you have is equal to the number of different states that the environment can be in. In examples like this, remember that here what we are doing is something that's very special. We are thinking of a process in which you're starting with some product state of your system and the environment, and then you're asking, well, whatever is the process of interaction, that what are the different states that it puts the environment in, given that your initial state was this product state, and then the number of Krauss operators happens to be the number of different environment states that are involved in the process. But the interaction may not always be describable in this form, meaning in terms of the action on a starting product state of your system and the environment. Sometimes the interaction is also described in terms of what happens to an entangled state of your system and the environment, in which case there's a more general procedure to obtain these Krauss operators, which I'm not going to go into, but you can find that in most textbooks on quantum, most good textbooks on quantum information, for instance, Nielsen and Huang or something. Okay, so all right, so on the clock I have 2 minutes. We started about 5 or 6 minutes late, so I could either just stop here or I could go on for another 10 minutes or so, your choice. I mean, I will absolutely not feel offended if you say that stop here, we've had enough. So yeah, maybe I'll just do that. The other thing which I have in my notes was to use this amplitude damping formalism to show you what happens when you couple a harmonic oscillator to an electromagnetic field, to photons, and how dephasing happens there, and how, when you have a macroscopic object, something that's very large, and you put it in contact with an environment, it dephases immediately. So one of the reasons out of many reasons, that quantum mechanics doesn't apply to me and you, or rather, when you're seeing me, you're not seeing a superposition of me here and there, right? The reason that doesn't happen, and it can't happen, is that I'm a macroscopic object, and even if miraculously you were able to create such a superposition of me 1 over square root of 2 me here plus 1 over square root of 2 me there, and I was exposed to an environment, I would immediately dephase, right? And that information would go away. So that was there in a simple calculation, but I can just leave that in the notes for you to understand for yourselves. Okay, so thanks a lot. Thank you very much for your patience and for listening. And if you have any questions, I'll be happy to answer them.
I thought you were going to continue.
Oh, you want me to continue? I'm happy to. I mean, that's. Oh, okay. Okay, fine. All right. I see. Okay. Okay, fine. So let me try to make this quick. So what we have here is we just had a single qubit, and so if you look at the states of the single qubit, so there's a 0 state and a 1 state. That's it. And then we had this amplitude damping and dephasing for a system of just these 2 states. So imagine now that I have a harmonic oscillator. So this amplitude damping process that I told you about, where what we are saying, it really is describing the spontaneous emission of something from an excited state to a ground state, releasing a photon. One could generalize this to a system in which you had more than two states. So imagine that you have a harmonic oscillator right? And so if you look at the spectrum of the harmonic oscillator, so that has these equally spaced states. So this is n equal to 0, n equal to 1, n equal to 2, and so on. And one can also talk about spontaneous emission in this case. So our system now is not a qubit anymore. It's not some two-dimensional system. It's actually an infinite dimensional harmonic oscillator. And we can, just for simplicity, think of processes where you're looking at the spontaneous emission of, so the harmonic oscillator, let's say, is in some particular state, let's say this one, and then it makes a transition to the state immediately below it, which is h bar by omega below it in energy, and releases a photon. Okay. So that can happen for any of these states. So let's just look at that sort of process. So that photon is going into the environment. And so let's look at that kind of process and see what that means in terms of amplitude damping and dephasing for the harmonic oscillator. So just to be concrete, so if you only had the harmonic oscillator and no environment, then this would be the Hamiltonian of the system. Now we have an environment, it interacts with the environment. And so here I'm actually going to write down a Hamiltonian for the interaction. So the Hamiltonian for the interaction is going to be of this form: G times A hat B hat dagger plus A hat dagger B hat, where A and A hat are the ladder operators of the harmonic oscillator, B hat and B are the creation and annihilation operators for the photons. So you can see from this interaction term that the action of the first term is to lower the quantum number of the harmonic oscillator by 1, that's the annihilation operator, and at the same time create a photon, whereas the other one does the opposite, right? That it increases the quantum number of the harmonic oscillator by 1 and destroys a photon. So this is like emission of a photon, this is like absorption of a photon. We'll really be interested in this process. So incidentally, for those of you who might have worked on this kind of thing, this is also the sort of term that you get in something called the Jaynes-Cummings model. Except that in the Jaynes-Cummings model, you aren't really thinking of a harmonic oscillator, it's really a two-level system that's coupled to a bath of photons. And so these are not ladder operators for a harmonic oscillator, but rather the sigma plus and sigma minus operators for a two qubit system. Okay, fine. So this is what we have, and we are looking at the emission process. So the emission process, in the kind of language that we described earlier, is of this sort. So excuse me. So if you were in the ground state, nothing would happen. If the harmonic oscillator was in the first excited state, then it would make a transition to the ground state with probability p and remain in the first excited state with probability 1 minus p. So it's just like what we'd written down earlier for the two-level system. And this 1e state here is really the state of the environment with a single photon in it. The 0e state here is the state of the environment with no photon in it. So we can keep going. So now if you look at the 2a state, and remember that this interaction is because of this Hamiltonian. So if the harmonic oscillator was in the 2a state, right, then the interaction would produce the following. It would produce square root of 1 minus 2p 2a 0e plus square root of 2p 1a 1e. And in case you're wondering where the square root of 2 came from, that actually comes from the action of the annihilation operator. Okay? And so if you were in the 3a 0e state, then this would be square root of 1 minus 3p 3a 0e plus square root of 3p 2a 1e and so on. So now clearly you can see from this that if I were to write it like this, it wouldn't be meaningful beyond a certain value of n if I had some fixed probability p, because soon enough these things, what would happen is that if your n became large enough, then these would become negative and this would be meaningless. So this kind of process you can only treat in the continuum time approximation, where you're assuming that there is some rate of transition, so p is equal to gamma times delta t, and you're taking the limit delta t going to 0, and then you're fine, right? We're doing this. Okay, so this is our process, and so once again you can see that we only have two Krauss operators. Yeah.
So third case, why are we excluding this double photon emission?
Sorry, why are we considering?
Not considering the double photon emission, like
Thermal photon. Double. Okay, we're just to keep things simple. Okay. So as I said, I mean, so this is just to keep the discussion simple. You're absolutely right. In principle, one could do that. So the only thing is that if you consider a double photon emission, let's say you're jumping from n equal to 2 to n equal to 0, then you're releasing a photon with a frequency which is 2 omega instead of omega, right? Or you're releasing 2 photons of omega. So we are not looking at any 2 photon process. It turns out that the problem with the 2 photon process is that it's not strictly Markovian. And if it's a single 2 omega process, then it's going into a different environment with a different frequency. And so we're just ignoring all of that to keep the discussion simple. Okay, so here what we have is we again have two Krauss operators because there are only two states of the environment, 0 and 1. So because we are going to do this in, the only way in which this is meaningful is in this continuous time way. So we have to treat this using the Lindblad equation. And so it just turns out, so if you write down what the Krauss operators are and then correspondingly write down what the jump operators are, what you will find is that in the Lindblad equation, which I had written down earlier, let me not write down the whole thing again just for the sake of time. You just have the Hamiltonian H, which is h bar omega a hat dagger a hat plus 1/2. Okay, so you have that in the Lindblad equation, and you have this. So this is the only thing in the first Krauss operator. It's just the Hamiltonian. The second Krauss operator just gives you one Lindblad jump operator, and that one single Lindblad jump operator is square root of gamma times the annihilation operator. So this is it. So this is all that you need to plug into the Lindblad equation. And so you can plug this into the Lindblad equation, solve what you can get something for the density matrix, right? How the density matrix evolves. But it just turns out that to see what's happening physically here, it's more meaningful to look at the Lindblad evolution for the operator, using the operator equation rather than the density equation. And you'll see why in just a second. So remember that the operator equation was dO hat dt is equal to I h bar plus, in this case, with this one single Lindblad jump operator, the operator equation ends up being a hat dagger O hat A hat minus 1/2 anti-commutator of A hat dagger A hat O hat. Okay. And H is this. So let me choose O hat in this case to just be the annihilation operator itself. Let me see how the annihilation operator evolves as a function of time. There's nothing in this equation which tells me that the operator in question has to be a Hermitian operator. Okay, so you can plug that in, do all the algebra, and so again in the interest of time, let me just tell you what the answer is. So the answer is quite simple. It turns out that the annihilation operator is a function of time, goes as e to the minus I omega minus I gamma by 2 t a hat. So that was the evolution of the annihilation operator if you plug this in here. So if you now look at what happens to the occupation number operator. So remember that the number operator is at time t is a hat dagger t a hat t. So we can just take the dagger of this and get a hat dagger t, and from that we can get the evolution of the number operator. So from this you can just see that the number operator, this goes as e to the minus gamma t n hat of 0, and that's not surprising, right? Because no matter what state you started from, eventually it's going to fall down to the ground state. Okay, but here's the thing about, okay, now, so the last thing is the stuff that I told you about macroscopic objects and how you can't create superpositions of those. So imagine now that I'm looking at what happens to a coherent state. So imagine that your initial state was actually a coherent state as opposed to some particular eigenstate. So a coherent state of a harmonic oscillator is of this form. So I hope all of you are familiar with coherent states. So that's the coherent state of a harmonic oscillator. And in this coherent state, if you were to ask what the expectation value is of the displacement of the oscillator, then that turns out to be square root of 2 h bar m omega alpha cosine theta, mod alpha cosine theta, if alpha is mod alpha e to the I theta. Okay. So you can go ahead, turn the crank and ask, well, if your initial state was a coherent state, what would the evolution be like? Write down the density matrix for this, put that into the Lindblad equation, ask what the evolution would be, and you'll see that the evolution would be that your initial coherent state would just evolve into something like this. Another coherent state, but now instead of alpha, it would be alpha e to the minus I omega t e to the minus gamma t by 2. And so you can see as time progresses, basically this goes to 0. And so that tells you that your displacement is going to 0 as time progresses, right? It goes to infinity, and that's fine because that's exactly what this is supposed to do. It's damping your harmonic oscillator. Your energy is going away. So if it had some initial displacement and this was the dynamics, the gamma would be like a damping term, and so it would be oscillating and damping and eventually go to 0. Fine. But here's the interesting thing. Now imagine that you had another coherent state, beta, which is e to the minus mod beta squared by 2 e to the beta alpha hat e to the sorry alpha a dagger acting on the vacuum state. And suppose you look, so this again, if you ask what is the displacement x hat corresponding to this, you just have mod beta and whatever is the cosine of the phase angle for this coherent state here. But the important thing is, if you were to look at the overlap between these two coherent states, then you can show that this is the exponential of minus mod alpha minus beta squared. Okay. So here now is the final thing. So suppose you started the system out in a superposition of these two coherent states. Okay. So suppose I started the system out in a superposition of, let's say, just to keep things simple, an equal amplitude superposition of these two coherent states, alpha and beta. And this is exactly the kind of state that Arnav was talking about in a different context. It's called a cat state. Okay. So in particular, if let's say you took beta to be equal to minus alpha, then this would be a superposition of two different coherent states. One that would be centered about some x, and the other that would be centered about minus x. Okay. So now you take a superposition of two coherent states, one centered about x, one centered about minus x, and you ask, well, what happens to that as Yeah, so this is, let's say, one coherent state here, the other coherent state here, and you're taking a superposition of these two. And then, so that's your initial state, and you let it evolve. According to this, what would happen? So what would happen is that, of course, you would have a damping individually of the alpha and the beta in that way, but you would also have dephasing. So in the density matrix that you would create from these states, if you were to look at how a term like this in the density matrix would evolve under this evolution, you would see that it would go as some there's some phase which is not important, and then there's going to be the dephasing term, e to the minus gamma t mod alpha minus beta squared by 2 times this, where alpha of t is what I wrote down here. This was alpha of t, and similarly beta of t. So that's what happens. And the important thing is that you have this thing here which is causing the dephasing now. And so the time scale over which you have dephasing, or the rate of dephasing, gamma d, so the rate of dephasing, which would be your T2, is in this case 1/2 gamma mod alpha minus beta squared. Okay? So that's your dephasing rate. And you can see that depending on what alpha and beta are, your dephasing rate is now no longer, gamma by 2. So your T2 is no longer T1 by 2, it could be something else. And it could actually, as I'll show you in just a minute, it can turn out to be a pretty much larger than gamma, so things can dephase very quickly. Okay, so the very last, very quick back of the envelope calculation is, so this is what would happen in this particular situation, where you're assuming that the environment is such that there's either no photon in it or there's one photon in it. So now we come to something that's slightly more general, in the sense that imagine that your environment was of the sort where if there is no spontaneous emission, there is still some thermal bath of photons. So the environment is in some equilibrium at temperature T. And then on top of that, if you have spontaneous emission, you get an extra photon. So in that case, what will happen is that if the temperature of your environment, just to keep things simple again, is much larger than h bar by omega, then the average occupancy of photons in the environment is going to be about kBt by h bar omega, just coming from the Bose factor. Okay? So in a situation like that, if that was your situation, then your gamma d by gamma would get an enhancement by this factor. So your gamma d by gamma would go as mod of alpha minus b whole squared kBt by h bar omega, and this would depend on what the temperature is. So further, if you actually started with this cat state where something was at plus x and something was at minus x, then mod of alpha minus beta would basically go as square root of m omega by 2 h bar times x. So the alpha state is localized at x, this is at minus x, and you get this. So let's just put everything in here, and then we have our final answer, which is that you would find that gamma d by gamma is going to go as x squared divided by lambda t squared, and the lambda t here is exactly the quantity that was also there in Professor Kampa's lecture, which is the thermal de Broglie wavelength. So lambda t is the thermal de Broglie wavelength. And so for a macroscopic object, okay, so this is where the macroscopic part comes in. Like me, for instance, okay, what you would find is that any reasonable length scale over which you might want to put me in superposition, for instance, like the extent of my body or something, that length scale divided by the thermal de Broglie wavelength would be very, very large. So which means that the dephasing rate is actually going to be huge. And so even if you did put me in that kind of superposition, right, me here plus me there, 1 over square root of 2 over that distance, the dephasing would be so quick that the phase information would just be lost immediately. So that's the reason that putting macroscopic objects in some quantum superposition is so hard, because that superposition would immediately dephase because of the environment. And so this is an example of that. There are also many other ways in which you can do this. Okay, so I'll end here. So once again, thank you very much for your patience and for staying till the end. Thanks a lot.
To you for attending this whole school, and I'll ask Shami to just conclude this session. Yeah.
Don't need, I guess, this one. Yeah. Someone is. Huh? Someone has gone. So first of all, thank you very much for coming into the school. I think you learned, we all learned a lot from the lecturers. Thanks to all the lecturers that they agreed to come, lecturers from abroad as well as the ones from India. And well, I look forward to welcoming you here again in the future school. I would like to especially thank Samavanti. He doesn't seem to be here at the moment, but he had been the most attentive of all participants because he was there, video recording all the lectures, and so he was on time and he was there till the end. So, and also to our computer staff, our admin staff, some of them are there, our canteen staff, and last but foremost, my students who were the real co-organizers of this school, Vidyarshav, Manish, Shelkop, and Shomo. Shomo is okay. So a big round of applause to everyone.
And also a very big round of applause to Shomya. Thank you for the wonderful job.